question, there's a long insulating solid cylinder with the given radius. It's charged, it has a positive charge, and it's concentric with a conducting cylindrical shell, which is also charged, and that has an inner and outer radius given. We'd like to find the surface charge densities on the conductor, the electric field inside and outside of the cylinder, and make a sketch of the electric field. First, let's draw a picture of what's happening here. We'll do a 3D picture first. We have a solid insulator, so something like this, a long solid insulator. So this is the insulator. Around the insulator is a conducting shell. So let's draw that guy next. And the conducting shell has a thickness. So it's not a thin shell, it's a thick shell. So let's try and draw something like this for our conducting shell. Okay, maybe not the best picture, but hopefully it's kind of okay. There. So there's our conductor. And so this is the conductor right here. This part is solid. In between the conductor and the insulator is nothing. There's just a vacuum in there. That's a 3D version. We can also draw a two-dimensional version. So an edge view. In the edge view, we have the insulator right here in the center, and it's surrounded by the conductor. Like this. Okay, so there's a picture of what we have. The first thing we want to find are the inner and outer surface charge densities of the conductor. We want to find the charge density that's right here, that's on the inner part, or along right here. The charge density that's on the outer part, that's out right here. It says surface charge density, so that means charge divided by area. So we'll start there. What we mean by charge density, surface charge density, is the symbol eta, which is charge over area. So the charge density on the inner surface is going to be the charge on the inner surface divided by the area of the inner surface. So if we have our insulator here, our conductor here, like this. So what is the charge density right here? QI equals. So let's do the area first, because the area is not that hard to do. So if our conductor has a length L, then the area of the inner surface will be 2 pi times the radius of the inner surface times the length. So there's the area of the inner surface. Now let's see, what is the charge on the inner surface? Well, we're going to have to figure that out using Gauss's law. I'm going to go back to the two-dimensional picture here. So there's the insulator. Here's the conductor. And we should draw a Gaussian surface if we're going to try and figure out something about the charge. I'm going to draw a Gaussian surface that's a cylinder located within the conducting cylindrical shell. So there's my Gaussian surface. It's right inside the conducting shell. So the Gaussian surface is cylinder inside the conducting shell. That has a radius that we'll call little r. So if we write down Gauss's law, we know that the net electric flux is the integral of E dot dA equals Q inside over epsilon naught. So this is charge inside the Gaussian surface. Well, what we know is that the electric field inside a conductor equals 0. So that tells us that the Q inside the Gaussian surface equals 0. So that's 0 because the electric field in the conductor is 0. So how does that help us find the charge on the inner surface? So the charge on the inner surface we called Qi. Well, the net charge inside the Gaussian surface is equal to whatever charge is on the inner surface of the conducting shell, Qi, plus whatever charge is on the insulator. We'll call that QINS for insulator. So let's put these two things together. 0 is equal to the net charge on the inner surface of the conductor plus the charge of the insulator. So the charge on the inner surface of the conductor is the negative of the charge on the insulator. So that gives us a net charge of 0 inside of our Gaussian surface, which gives us an electric field of 0 inside our conducting shell, which makes sense because conductors in static equilibrium have 0 electric field inside. So the last bit we have to sort out is what is the charge on our insulator right here. Well, we know the volume charge density of the insulator is rho, and to get charge we would do density times volume. And I'll write down volume of the insulator here just to remind ourselves that we mean the insulator. So the volume of our insulator is pi r squared times L, times the length of the insulator. Okay, so now in our picture, just to make sure we remember what we're talking about, that's R, this is R. So there's the charge inside on the inner surface of the conducting shell. Let's put that together with our expression for our charge density and find what the charge density is equal to. So the charge density on the inner surface of the conducting shell is the charge on the inner surface of the conducting shell divided by the area, negative of the charge density of the insulator times pi times the radius of the insulator squared times the length of the insulator, divided by the area of the inner surface of the conducting shell, 2 pi times the radius of the inner surface of the shell times L. See that the L's cancel, pi's cancel, and what we are left with is minus rho times r squared divided by 2 times r of the inner surface. We can put our numbers in here. The charge density of the insulator is 3 times 10 to the minus 4 coulombs per meter cubed. R is the radius of the insulator, 5 centimeters, divided by 2 times the radius of the inner surface of the conducting shell, 7.5 centimeters. Put that through the calculator and we get a charge density of minus 5 times 10 to the minus 6 coulombs per meter squared. So there's the charge density on the inner surface of the conducting shell. We're also asked for the charge density on the outer surface. So the charge density on the outer surface is the charge on the outer surface divided by the area of the outer surface. So there's the insulator, there's the conductor, so we want to find what is Q on the outer surface. So let's see what we know about this. If we want to find the charge on the outer surface, what we know is that the Q for the conductor, so the net charge on conductor, is whatever charge is on the outer surface plus whatever charge is on the inner surface. So let's see what we know here. We're given in the problem that the conducting shell has a net charge per unit length of minus 4.25 times 10 to the minus 6. So the net charge on the conductor, Q of the conductor, would be the charge density times the length. So there's the net charge on the conductor. The net charge on the inner surface we found in the previous step. So we found the net charge on the inner surface. So now we can solve for the net charge on the outer surface. So the net charge on the outer surface is the net charge on the conductor, take away whatever is on the inner surface. So on the conductor is lambda times L. We're going to subtract what we found that was on our inner surface. So minus a minus rho times pi r squared L. So there's our net charge on the outer surface of that conducting shell. We can just make this look a little bit nicer. Lambda L plus rho pi r squared L. And our area of our outer surface, so this has a radius of r for the outer surface. So the area of the outer surface is equal to 2 pi r for the outer surface times the length. So there's the area for the outer surface. So let's put these things together to find the total charge density on the outer surface. So our charge is lambda times L, so that's our charge density on the conducting shell, plus rho pi r squared L, that's the charge on the inner surface, divided by 2 pi r o L. So our L's cancel. We're left with lambda plus rho times pi times r squared divided by 2 pi r for the outer surface. We can plug in our numbers here. Our lambda, our linear charge density, is minus 4.25 microcoulombs per meter. Plus charge density, volume charge density rho, which is 3 times 10 to the minus 4 coulombs per cubic meter. Times pi times r. Remember, this is the radius of the insulator, so that's our 5 centimeters. Then we're dividing that by 2 times pi times the radius of the outer surface of the conducting cylinder, which is 8 centimeters. Put all that through the calculator, and what we get for our answer is minus 3.77 times 10 to the minus 6 coulombs per meter squared. So there is the surface charge density on the inner and outer surface of that conducting shell. So the shell is charged, it's a conductor, so the charge has to reside either on the inner surface or the outer surface. So we get some charge on both, and there's the density of each side. So next we'll move on to finding the electric field in all the spots.